All right, let's get started. Oh my gosh, I'm so tired already, though. Okay, I'm gonna go ahead and get into some chemistry. I think I have that actually. Nope, I don't. So, Openstax. It's annoying that they changed this website. Chemistry. 2E. Download PDF. File. I think I'm on chapter 9 or 10. Let's, where am I at? Oh, here. Sociology. TUI. Yep, Openstax Chemistry 2E9. So I'm chapter 10. I'm going to go ahead and log out of this. And I'm going to back out. Yep. 2E. 10. Zoom out. Okay, chapter 10. Openstax Chemistry. Liquids and solids. Chapter outline 10.1 Intermolecular forces, or as we like to call it, IMFs. 10.2 Properties of liquids. 10.3 Phase transitions. 10.4 Phase diagrams. 10.5 The solid state of matter. 10.6 Lattice structures in crystalline solids. Introduction. Leprosy has been a devastating disease throughout much of human history. Oh, hold on. There we go. All right. Let's get that Dragon Age Inquisition main menu theme rolling. All right, introduction. Leprosy has been a devastating disease throughout much of human history. Aside from the symptoms and complications of the illness, its social stigma led sufferers to be cast out of the communities and isolated in colonies. In some regions, this practice lasted well into the 20th century. At that time, the best potential treatment for leprosy was oil from the chamugra tree. But the oil was extremely thick, causing blisters and making usage painful and ineffective. Healthcare professionals seeking a better application. I'm going to turn this up all the way. There we go. Better application. Contacted Alice Ball, a young chemist at the University of Hawaii, who had focused her master's thesis on a similar plant. Ball initiated a sequence of procedures, repeated acidification and purification, to change the characteristics of the oil and isolate the active substances, esters discussed later in this text. The Ball method, as it later became to be called, became the standard treatment for leprosy for decades. In the liquid and solid states, atomic and molecular interactions are of considerable strength and play an important role in determining a number of physical properties of the substance. For example, the thickness or viscosity of chalmugra oil was due to its intermolecular forces. In this chapter, the nature of these interactions and their effects on various physical properties of liquid and solid phases will be examined. 10.1. Intermolecular forces. By the end of this section, you'll be able to describe the types of intermolecular forces possible between atoms and molecules in condensed phases, dispersion forces, dipole-dipole attractions, and hydrogen bonding. I swear, they change the name of these things every freaking time. Identify the types of intermolecular forces experienced by specific molecules based on their structures. Explain the relation between the intermolecular forces present within a substance and the temperatures associated with changes in its physical state. As was the case for gaseous substances, the kinetic molecular theory may be used to explain the behavior of solids and liquids. Hold on one sec. I'm going to pause for a sec. Back to that. In the following description, the term particle will be used to refer to an atom, molecule, or ion. Note that we will use the popular phrase intermolecular attraction to refer to attractive forces between the particles of a substance, regardless of whether these particles are molecules, atoms, or ions. Consider these two aspects of the molecular level environment in solids, liquids, and gaseous matter. Particles in a solid are tightly packed together and often arranged in a regular pattern. In a liquid, they are close together with no regular arrangement. In a gas, they are far apart with no regular arrangement. Particles in a solid vibrate about fixed positions and do not generally move in relation to one another. In a liquid, they move past each other but remain in essentially constant contact. In a gas, they move independently of one another except when they collide. The differences in the properties of a solid, liquid, or gas reflect the strengths of the attractive forces between the atoms, molecules, or ions that make up each phase. The phase in which a substance exists depends on the relative extent of its intermolecular forces. Sorry. Let's see. The differences in the properties of a solid, liquid, or gas reflect the strengths of the attractive forces between the atoms, molecules, or ions that make up each phase. The phase in which a substance exists depends on the atoms, molecules, or ions that make up each phase. The phase in which a substance exists depends on the relative extent of its intermolecular forces and the kinetic energies of its molecules. IMFs are the various forces of attraction that may exist between the atoms and molecules of a substance due to electrostatic phenomena, as will be detailed in this module. Oh, 3,200, geez. These forces serve to hold particles close together, whereas the particle's kinetic energy provides the energy required to overcome the attractive forces and thus increase the distance between particles. Figure 10.2 illustrates how changes in physical state may be induced by changing the temperature, hence the average kinetic energy of a given substance. As an example of the processes depicted in this figure, consider a sample of water. When gaseous water is cooled sufficiently, the attractions between H2O molecules will be capable of holding them together when they come out into contact with each other. The gas condenses, forming liquid H2O. For example, liquid water forms on the outside of a cold glass as the water vapor in the air is cooled by the cold glass, as seen as figure 10.3. We can also liquefy many gases by compressing them if the temperature is not too high. The increased pressure brings the molecules of a gas closer together, such that the attractions between the molecules become strong relative to their kinetic energy. Consequently, they form liquids. Butane C4H10 is the fuel used in disposable lighters and is a gas at standard temperature and pressure. Inside the lighter's fuel compartment, the butane is compressed to a pressure that results in its condensation to the liquid state, as shown in figure 10.4. Finally, if the temperature of a liquid becomes sufficiently low, or the pressure on the liquid becomes sufficiently high, the molecules of the liquid no longer have enough kinetic energy to overcome the IMF between them, and a solid forms. A more thorough discussion of these and other changes of state or phase transitions is provided in a later module in this chapter. Forces between molecules. Under appropriate conditions, the attractions between all gas molecules will cause them to form liquids or solids. This is due to intermolecular forces, not intramolecular forces. Intramolecular forces are those within the molecule that keep the molecule together, for example, the bonds between the atoms. Intermolecular forces are the attractions between molecules, which determine many of the physical properties of a substance. Figure 10.5 illustrates these different molecular forces. The strength of these attractive forces vary widely, though usually the IMFs between small molecules are weak compared to the intermolecular forces that bonds atoms together within a molecule. For example, to overcome the IMFs in 1 mole of liquid HCl and convert it into gaseous HCl requires only about 17 kilojoules. However, to break the covalent bonds between the hydrogen and chlorine atoms in 1 molecule of HCl requires about 25 times more energy, 430 kilojoules. All of the attractive forces between neutral atoms and molecules are known as van der Waals forces, although they are usually referred to more informally as intermolecular attraction. We will consider the various types of IMFs in the next 3 sections of this module. Dispersion forces. One of the 3 van der Waals forces is present in all condensed phases, regardless of the nature of the atoms or molecules composing the substance. This attractive force is called the London dispersion force in honor of German-born American physicist Fritz London, who, in 1928, first explained it. This force is often referred to as simply the dispersion force. All right, one sec. All right. This force is often referred to as simply the dispersion force because the electrons of an atom or molecule are in constant motion, or alternatively, the electron's location is subject to quantum mechanical variability. At any moment in time, an atom or molecule can develop a temporary instantaneous dipole. If its electrons are distributed asymmetrically, the presence of this dipole can, in turn, distort the electrons of a neighboring atom or molecule, producing an induced dipole. These 2 rapidly fluctuating temporary dipoles thus result in relatively weak electrostatic attraction between the species, a so-called dispersion force like that illustrated in figure 10.6. Dispersion forces that develop between atoms and different molecules can attract the 2 molecules to each other. The forces are relatively weak, however, and become significant only when the molecules are very close. Larger and heavier atoms and molecules exhibit stronger dispersion forces than do smaller and lighter atoms and molecules. Fluorine and chlorine are gases at room temperature, reflecting weaker attractive forces. Bromine is a liquid and iodine is a solid, reflecting stronger attractive forces. Trends in observed melting and boiling points in halogens clearly demonstrate this effect, as seen in Table 10.1. The increase in melting points with increasing atomic molecular size may be rationalized by considering how the strength of dispersion forces is affected by the electronic structure of the atoms or molecules in the substance. In a large atom, the valence electrons are, on average, farther from the nuclei than in a smaller atom. Thus, they are less tightly held and can more easily form the temporary dipoles that produce the attraction. The measure of how easy or difficult it is for another electrostatic charge, for example, a nearby ion or polar molecule, to distort a molecule's charge distribution, is known as polarizability. A molecule that has a charge cloud that is easily distorted is said to be very polarizable and will have large dispersion forces. One with a large cloud that is difficult to distort is not very polarizable and will have small dispersion forces. The shapes of molecules also affect the magnitudes of the dispersion forces between them. For example, boiling points for the isomer N-pentane, isopentane, and neopentane are 36 degrees, 27 degrees, and 9.5 degrees respectively. Even though these compounds are composed of molecules with the same chemical formula, C5H12, the difference in boiling point suggests that dispersion forces in the liquid phases are different, being greatest for N-pentane and least for neopentane. The elongated shape of N-pentane provides a greater surface area available for contact between molecules, resulting in correspondingly stronger dispersion forces. The more compact shape of isopentane offers a smaller surface area available for intermolecular contact, and, therefore, weaker dispersion forces. Neopentane molecules are the most compact of the three, offering the least available surface area for intermolecular contact, and hence the weakest dispersion forces. Their behavior is analogous to the connections that may be formed between strips of Velcro brand fasteners. The greater the area of the strip's contact, the stronger the connection. Oops. Dipole-dipole attractions. Recall from the chapter on chemical bonding and molecular geometry that polar molecules have a partial positive charge on one side and a partial negative charge on the other side of the molecule, a separation of charge called a dipole. Consider a polar molecule such as hydrogen chloride, HCl, in the HCl molecule. The more electronegative Cl atom bears the partial negative charge, whereas the less electronegative H atom bears the partial positive charge. An attractive force between HCl molecules results from the attraction between the positive end of one HCl molecule and the negative end of another. This attractive force is called dipole-dipole attraction, the electrostatic force between the partially positive end of one polar molecule and the partially negative end of another, as illustrated in Figure 10.9. The effect of a dipole-dipole attraction is apparent when we compare the properties of HCl molecules to the nonpolar F2 molecules. Both HCl and F2 consist of the same number of atoms and have approximately the same molecular mass. At a temperature of 150 Kelvin, molecules of both substances would have the same average kinetic energy. However, the dipole-dipole attractions between HCl molecules are sufficient to cause them to stick together to form a liquid, whereas the relatively weaker dispersion forces between nonpolar F2 molecules are not, and so this substance is gaseous at this temperature. The higher normal boiling point of HCl compared to F2 is a reflection of the greater strength of dipole-dipole attractions between HCl molecules compared to the attractions between nonpolar F2 molecules. We will often use values such as boiling or freezing points or enthalpies of vaporization or fusion as indicators of the relative strengths of IMFs of attraction present within different substances. Hydrogen bonding. Nitrosyl fluoride is a gas at room temperature. Water is a liquid, even though it has a lower molecular mass. We clearly cannot attribute this difference between the two compounds to dispersion forces. Both molecules have about the same shape, and O&F is heavier and larger molecule. It is therefore expected to experience more significant dispersion forces. However, we cannot attribute this difference in boiling points to differences in the dipole moments of the molecules. Both molecules are polar and exhibit comparable dipole moments. The large difference between the boiling points is due to a particularly strong dipole-dipole attraction that may occur when a molecule contains a hydrogen atom bonded to a fluorine atom, oxygen, or nitrogen atom, the three most electronegative elements. The very large difference in electronegativity between the H atom and the atom to which it is bonded, combined with the very small size of the H atom and relatively small sizes of fluorine, oxygen, and nitrogen atoms, leads to a highly concentrated partial charges of these atoms. Molecules with FH, OH, and NH moieties are very strongly attracted to similar moieties in nearby molecules, a particularly strong type of dipole-dipole attraction called hydrogen bonding. Examples of hydrogen bonds include HF, HF, H2O, HOH, and H3N, HNH2, in which the hydrogen bonds are denoted by dots. Figure 1010 illustrates hydrogen bonding between water molecules. Despite use of the word bonds, keep in mind that hydrogen bonds are intermolecular attractive forces, not intramolecular attractive forces. Hydrogen bonds are much weaker than covalent bonds, only about 5 to 10% as strong, but are generally much stronger than other dipole-dipole attractions and dispersion forces. Hydrogen bonds have a pronounced effect on the properties of condensed phases. For example, consider the trends and boiling points for the binary hydrides of group 15, so NH3, PH3, ASH3, and SPH3. Group 16 hydrides, H2O, H2S, H2SE, and H2TE, and group 17 hydrides, HF, HCl, HBr, and HI. The boiling points of the heaviest three hydrides for each group are plotted in figure 1011. As we progress down any of these groups, the polarities of the molecules decrease slightly, whereas the sizes of the molecules increase substantially. The effect of increasingly stronger dispersion forces dominates that of increasingly weaker dipole-dipole attractions, and the boiling points are observed to increase steadily. If we use this trend to predict the boiling points for the lightest hydride for each group, we would expect NH3 to boil at about 120 degrees Celsius, H2O to boil at about 80 degrees Celsius, and HF to boil at about 110 degrees Celsius. However, when we measure the boiling points for these compounds, we find they are dramatically higher than the trends would predict, as shown in figure 1012. The stark contrast between our naive predictions and reality provides compelling evidence for the strength of hydrogen bonding. Okay. Pause. All right, I'm back. That took a little bit longer than I wanted it to, but not much I could do about that. Okay. So it's been about 3 hours. 2 hours. Okay. 10.2 Properties of liquids. But first, let's get my headphones on. Properties of liquids. By the end of the section, you will be able to distinguish between adhesive and cohesive forces, define viscosity, surface tension, and capillary rise, describe the roles of intermolecular attractive forces in each of these properties and phenomena. When you pour a glass of water or fill a car with gasoline, you observe that water and gasoline flow freely. When you pour syrup and pancakes or add oil to a car engine, you note that the syrup and motor oil do not flow as readily. The viscosity of a liquid is a measure of its resistance to flow. Water, gasoline, and other liquids that flow freely have a low viscosity. Honey, syrup, motor oil, and other liquids that do not flow freely, like those shown in figure 10 to 15, have higher viscosities. We can measure viscosity by measuring the rate at which metal ball falls through a liquid, or by measuring the rate at which a liquid flows through a narrow tube. The IMFs between the molecules of a liquid, the size and shape of the molecules, and the temperature determine how easily a liquid flows. As Table 10.2 shows, the more structurally complex are the molecules in a liquid and the stronger the IMFs between them, the more difficult it is for them to move past each other, and the greater is the viscosity of the liquid. As the temperature increases, the molecules move more rapidly, and their kinetic energies are better able to overcome the forces that hold them together. Thus, the viscosity of the liquid decreases. The various IMFs between identical molecules of a substance are examples of cohesive forces. The molecules within a liquid are surrounded by other molecules and are attracted equally in all directions by the cohesive forces within the liquid. However, the molecules on the surface of a liquid are attracted only by about one half as many molecules. Because of the unbalanced molecular attractions on the surface molecules, liquids contract to form a shape that minimizes the number of molecules on the surface. That is, the shape with the minimum surface area. A small drop of liquid tends to assume a spherical shape as shown in figure 1016, because in a sphere, the ratio of surface area to volume is at a minimum. Larger drops are more greatly affected by gravity, air resistance, surface interactions, and so on, and as a result are less spherical. Surface tension is defined as the energy required to increase the surface area of a liquid, or the force required to increase the length of a liquid surface by a given amount. This property results from the cohesive forces between molecules at the surface of a liquid, and it causes the surface of a liquid to behave like a stretched rubber membrane. Surface tension of several liquids are presented in Table 10.3. Among common liquids, water exhibits a distinctly high surface tension due to strong hydrogen bonding between its molecules. As a result of this high surface tension, the surface of water represents a relatively tough skin that can withstand considerable force without breaking. A steel needle carefully placed on water will float. Some insects, like the one shown in figure 1017, even though they are denser than the water, move on its surface because they are supported by the surface tension. Surface tension is affected by a variety of variables, including the introduction of additional substances on the surface. In the late 1800s, Agnes Pockels, who was initially blocked from pursuing a scientific career but studied on her own, began investigating the impact and characteristics of soapy and greasy films in water. Using homemade materials, she developed an instrument known as a trough for measuring surface contaminants and their effects. With the support of renowned scientist Lord Rayleigh, her 1891 paper showed that surface contamination significantly reduces surface tension, and also that changing the characteristics of the surface, compressing and expanding it, also affects surface tension. Decades later, Irving Langmuir and Catherine Blodgett built on Pockels' work in their own trough and important advances in surface chemistry. Langmuir pioneered methods for producing single molecule layers of films. Blodgett applied these to the development of non-reflective glass, critical for filmmaking and other applications, and also studied methods related to cleaning surfaces, which are important in semiconductor fabrication. The IMFs of attraction between two different molecules are called adhesive forces. Consider what happens when water comes into contact with some surface. If the adhesive forces between the water molecules and the molecules of the surface are weak compared to the cohesive forces between the water molecules, the water does not wet the surface. For example, water does not wet waxed surfaces or many plastics, such as polyethylene. Water forms drops on these surfaces because the cohesive forces within the drops are greater than the adhesive forces between the water and the plastic. Water spreads out on glass because the adhesive force between water and glass is greater than the cohesive force within the water. When water is confined in a glass tube, its meniscus has a concave shape because the water wets the glass and creeps up the side of the tube. On the other hand, the cohesive forces between mercury atoms are much greater than the adhesive forces between mercury and glass. Mercury therefore does not wet glass, and it forms a convex meniscus when confined in a tube because the cohesive forces within the mercury tend to draw it into a drop. If you place one end of a paper towel in spilled wine, as shown in figure 1019, the liquid wicks up the paper towel. A similar process occurs in a cloth towel when you use it to dry off after a shower. These are examples of capillary action. When a liquid flows within a porous material due to the attraction of the liquid molecules to the surface of the material and to other liquid molecules, the adhesive forces between the liquid and the porous material, combined with the cohesive forces within the liquid, may be strong enough to move the liquid upward against gravity. Towels soak up liquids like water because the fibers of a towel are made of molecules that are attracted to water molecules. Most cloth towels are made of cotton, and paper towels are generally made from paper pulp. These both consist of long molecules of cellulose that contain many OH groups. Water molecules are attracted to these OH groups and form hydrogen bonds with them, which draws the water molecules up the cellulose molecules. The water molecules are also attracted to each other, so large amounts of water are drawn up the cellulose fibers. Capillary action can also occur when one end of the small diameter tube is immersed in a liquid, as illustrated in figure 1020. If the liquid molecules are strongly attracted to the tube molecules, the liquid creeps up the diameter of the tube, creeps up the inside of the tube until the weight of the liquid and the adhesive forces are in balance. The smaller the diameter of the tube is, the higher the liquid climbs. It is partly by capillary action occurring in plant cells called xylem that water and dissolved nutrients are brought from the soil up through the roots and into a plant. Capillary action is the basis for thin layer chromatography, a laboratory technique commonly used to separate small quantities of mixtures. You depend on a constant supply of tears to keep your eyes lubricated and on capillary action to pump tear fluid away. The height to which a liquid will rise in a capillary tube is determined by several factors as shown in the following equation. H equals 2 cap T cosine theta all over R rho G. In this equation, H is the height of the liquid inside the capillary tube relative to the surface of the liquid outside the tube. T is the surface tension of the liquid. Theta is the contact angle between the liquid and the tube. R is the radius of the tube. Rho is the density of the liquid. And G is the acceleration due to gravity, 9.8 meters per second squared. When the tube is made of a material to which the liquid molecules are strongly attracted, they will spread out completely on the surface, which corresponds to a contact angle of 0. This is a situation for water rising in a glass tube. 10.3. Phase transitions. By the end of this section, you will be able to define phase transitions and phase transition temperatures, explain the relation between phase transition temperatures and intermolecular attractive forces, describe the process represented by typical heating and cooling curves, and compute heat flows and enthalpy changes accompanying these processes. All right, I'm going to pause and take a break. All right. Let's get a little rain noise rolling. That one. Oh, man. Try it down a little bit, down a little bit, up a little bit. There. Rain sound. Oh, man. Now I'm sleepy. Only 7 though. So, all right. 10.3 phase transitions. By the end of this section, you will be able to define phase transition. I already read that. All right. We will witness and utilize changes of physical state or phase transitions in a great number of ways. As one example of global significance, consider the evaporation, condensation, freezing, and melting of water. These changes of state are essential aspects of our Earth's water cycle, as well as many other natural phenomena and technological processes of central importance to our lives. In this module, the essential aspects of phase transitions are explored. Vaporization and condensation. When a liquid vaporizes in a closed container, gas molecules cannot escape. As these gas phase molecules move randomly about, they will occasionally collide with the surface of the condensed phase, and in some cases, these collisions will result in the molecules re-entering the condensed phase. The change from the gas phase to the liquid is called condensation. When the rate of condensation becomes equal to the rate of vaporization, neither amount of the liquid nor the amount of the vapor in the container changes. The vapor in the container is then said to be in equilibrium with the liquid. Keep in mind that this is not a static situation, as molecules are continually exchanged between the condensed and gaseous phases, such as an example of a dynamic equilibrium, the state of a system in which the reciprocal processes, for example, vaporization and condensation, occur at equal rates. The pressure exerted by the vapor in equilibrium with a liquid in a closed container at a given temperature is called the liquid's vapor pressure, or equilibrium vapor pressure. The area at the surface of the liquid is in contact with the vapor, and the size of the vessel have no effect on the vapor pressure, although they do affect the time required for the equilibrium to be reached. You can measure the vapor pressure of a liquid by placing a sample in a closed container, like that illustrated in Figure 1022, and using a manometer to measure the increase in pressure that is due to the vapor in equilibrium with the condensed phase. The chemical identities of the molecules in a liquid determine the types and strengths of intermolecular attractions possible. Consequently, different substances will exhibit different equilibrium vapor pressures. Relatively strong intermolecular attractive forces will serve to impede vaporization as well as favoring recapture of gas phase molecules. When they collide with the liquid surface, resulting in a relatively low vapor pressure, weak intermolecular attraction present less of a barrier to vaporization and a reduced likelihood of gas recapture, yielding relatively high vapor pressures. The following example illustrates this dependence on vapor pressure on intermolecular attractive forces. As temperature increases, the vapor pressure of a liquid also increases due to the increased average kinetic energy of the molecules. Recall that at any given temperature, the molecules of a substance experience a range of kinetic energies with a certain fraction of molecules having a sufficient energy to overcome IMF and escape the liquid. At a higher temperature, a greater fraction of molecules have enough energy to escape from the liquid, as shown in Figure 1023. The escape of more molecules per unit of time and the greater average speed of the molecules that escape both contribute to the higher vapor pressure. Boiling points. When the vapor pressure increases enough to equal the external atmosphere pressure, the external atmospheric pressure, the liquid reaches its boiling point. The boiling point of a liquid is the temperature at which its equilibrium vapor pressure is equal to the pressure exerted on the liquid by its gaseous surroundings. For liquids in open containers, this pressure is due to the Earth's atmosphere. The normal boiling point of a liquid is defined as its boiling point when surrounding pressure is equal to 1 atmosphere. Figure 1024 shows the variation in vapor pressure with temperature for several different substances. Considering the definition of boiling point, these curves may be seen as depicting the dependence of a liquid's boiling point on surrounding pressure. Yeah. The quantitative relation between a substance vapor pressure and its temperature is described by the Clausius-Clapeyron equation. Pressure equals A, which is some constant, E, which is E, and then to the negative delta H vape over RT power, where delta H vape is the enthalpy of vaporization for the liquid, R is the gas constant, and A is the constant, whose value depends on the chemical identity of the substance. Temperature T must be in Kelvin in this equation. This equation is often rearranged into logarithmic form to yield the linear equation. All right. And then what you could do, cool thing, logarithmic form, so you take the natural log of both sides. Actually, that sounds like a fun little thing to do right now. Let's do it. Freaking love doing stuff like this. Let's put that there. All right, boys and girls, you ready to see some math? So, let's yoink Google Keep Up. And then get daily log. So this is 1013. Let's go ahead and silly me. I gotta plug in my USB. There we go. There we go. PP. Like this. Okay. 10, 13, 23, and it's 1927. And then just a couple notes. 120 instant. So set aside 30 for feed and 40 for gas. So that means I made 50 buckaroonies. All right. Let's do green. Let's do purple. Equation work will be done in purple because purple is my favorite color. Wrong one. So P equals A e to the negative delta H vape over R T. And just parentheses. So rule of logarithms. So if you have e to the x equals y, so to logarithmize, I'm going to call it that, ties me happen. It's going to be an arrow. So you do log e to the x, put that in parentheses, equals y, natural log of y. But another rule of log of e to the x equals x log e. So, we pull that, x natural log e equals y, but this is 1 by definition. So x equals natural log of y. So, doing it with that, we can take the natural log of both sides. ln p equals ln a e negative delta H T. And that's the same as saying another rule of logarithms, ln A B, if I remember right. I think that's right. Well, if that's the rule, I'm going to play with it. So ln P equals ln A plus ln E negative delta H vape RT. But remember that rule of logs, I could pull the whole exponent out. So I get ln P equals ln A minus delta H vape over RT ln E. That's 1. So we get ln P minus ln A equals negative delta H vape RT. I might have screwed up somewhere. Let's see. No, that's right. I don't have to worry about it anymore. This is the equation they have. Yep. So that's basically, I just wanted to show off that part. Pretty cool little thing. And then if you do it in If you decide to do it under two different circumstances, that's where these equations here, let me draw circles around these equations right here, and this one here. Okay. This linear equation may be expressed in a two-point format that is convenient for us to use. Oh, so basically what that's saying, and this will go back into the whole algebra thing. This is why I think you guys should follow me if you want to learn some of these things. So let's rewrite this. ln P equals ln A minus delta H vape over RT. And we have P equals A e to the negative delta H vape over T. So this is an exponential function. So it's going to look something like, so it's a negative sign, or something like, maybe like that. Been a while since I've done graphs, so that might be wrong, but that's close to, I think if I remember right, a positive exponential in green would be something like that, I think, if I remember right. So it starts out semi-linear for very, very small increments, but then it just freaking explodes. But this one here, this is like saying, so if this is your pressure axis, and this is your temperature axis, pressure, temperature, natural log of pressure, ln pressure. So the natural log of pressure is going to look something like, it's going to be more linear, or maybe it might be down. I don't know which way it's going to be. Probably down, because this is your x value. That's x. mx. That's b. That's y. You remember from your days, y equals mx plus b. So in this case, x equals 1 over temperature. M equals delta H vape over R negative. And then B equals ln A. So this is like an initial condition. And they said that this was dependent on the specific substance. So it's like the beginning. So without any change in enthalpy, this will be the starting value. And then the correction is this guy. So how much did we change it by? So that's pretty cool. So that's why algebra is important, especially if you decide to get into science. It's important to know how these equations were derived. And that is why I love math. Okay, anywho, let's go back. Since the constant A is the same, these two equations may be rearranged to isolate ln A and then set them equal to one another. So then you get this equation here, natural log of P2 over P1 equals delta H vape over R, and then the temperature conditions. So that's like saying the natural log of Y2 over Y1 equals negative M and then, because the slope should be the same, what this is saying is, let's write this down. So if you have two different points on a graph, let's say here and here, two lines. Let this one be P1. Let this one be P2. And that's the pressure. So the natural log of pressure, this is temperature, so the ln of P2 over P1 equals delta H vape over RT, sorry, not T, just over R, because this is just your constant term, over R. Is it 1 over T1 minus 1 over T2? Yep. So that's P1, P2, T1, T2. And so essentially it's saying that the difference between the reciprocals of these two positions multiplied by our m, by our slope, is going to equal the, I guess you could say it's like the logarithmic difference. Because ln, using that same rule, that's the same as ln P2 minus ln P1. Those two are equivalent. And so it's saying that the difference between the pressures equals the slope of the line and then some difference between the reciprocals of the temperatures. And so that's all based on experiment. So like you're not expected to know these things outright. Like these things, if you were to do an experiment with pressure and temperature, and then enthalpy, if we remember, delta H is defined as under constant P. So this would be like out just in the open air. Okay. Anywho, that was fun. Oh, I love doing stuff like that. I'm so happy I got to do that. All right. Enthalpy of vaporization. Vaporization is an endothermic process. The cooling effect can be evident when you leave a swimming pool or a shower. When the water on your skin evaporates, it removes heat from your skin and causes you to feel cold. The energy change associated with the vaporization process is the enthalpy of vaporization, or delta H vape. For example, the vaporization of water at standard temperature is represented by, and then there's the equation, and the associated enthalpy of vaporization. As described in the chapter of thermochemistry, the reverse of an endothermic process is exothermic, and so the condensation of a gas releases heat. That is correct. Melting and freezing. When we heat a crystalline solid, we increase the average energy of its atoms, molecules, or ions, and the solid gets hotter. At some point, the added energy becomes large enough to partially overcome the forces holding the molecules or ions in the solid in their fixed positions. And the solid begins the process of transitioning to the liquid state, or melting. At this point, the temperature of the solid stops rising, despite the continual input of heat, and it remains constant until all the solid is melted. Only after all the solid is melted will continued heating increase the temperature of the liquid. If we stop heating during melting and place the mixture of solid and liquid in a perfectly insulated container so no heat could enter and escape, the solid and liquid phases remain in equilibrium. This is almost the situation with the mixture of ice and water in a very good thermos bottle. Almost no heat gets in or out, and the mixture of solid ice and liquid water remains for hours. In a mixture of solid and liquid at equilibrium, the reciprocal processes of melting and freezing occur at equal rates, and the quantities of solid and liquid therefore remain constant. The temperature at which the solid and liquid phases of a given substance are in equilibrium is called the melting point of the solid, or the freezing point of the liquid. Use of one term or the other is normally dictated by the direction of the phase transition being considered, for example, solid to liquid or liquid to solid. The enthalpy of fusion and the melting point of a crystalline solid depends on the strength of the attractive forces between the units present in the crystal. Molecules with weak attractive forces form crystals with low melting points. Crystals consisting of particles with stronger attractive forces melt at higher temperatures. The amount of heat required to change 1 mole of substance from the solid state to the liquid state is the enthalpy of fusion. The amount of heat required to change 1 mole of a substance from the solid state to the liquid state is the enthalpy of fusion, delta H fuse, of the substance. The enthalpy of fusion of ice is 6 kilojoules per mole at 0 degrees Celsius. Fusion is an endothermic process. The reciprocal process, freezing, is an exothermic process whose enthalpy change is negative 6.0 kilojoules per mole at 0 degrees Celsius. Sublimation and deposition. Some solids can transition directly into the gaseous state, bypassing the liquid state via a process known as sublimation. At room temperature, the standard pressure, a piece of dry ice, solid CO2, sublimes, appearing to gradually disappear without ever forming any liquid. Snow and ice sublime at temperatures below the melting point of water, a slow process that may be accelerated by winds and reduced atmospheric pressures at high altitudes. When solid iodine is warmed, the solid sublimes and a vivid purple vapor forms. The reverse sublimation is called deposition, a process in which gaseous substances condense directly into the solid state, bypassing the liquid state. The formation of frost is an example of deposition. Like vaporization, the process of sublimation requires an input of energy to overcome intermolecular attractions. The enthalpy of sublimation, delta H sub, is the energy required to convert 1 mole of substance from a solid to the gaseous state. For example, the sublimation of carbon dioxide is represented by that equation. Likewise, the enthalpy change for the reverse process of deposition is equal in magnitude but opposite in sign to that for sublimation. Consider the extent to which intermolecular attractions must be overcome to achieve a given phase transition. Converting a solid into a liquid requires that these attractions be only partially overcome. Transition to the gaseous state requires that they be completely overcome. As a result, the enthalpy of fusion for a substance is less than its enthalpy of vaporization. This same logic can be used to derive an approximate relation between the enthalpies of all phase changes for a given substance. Though not an entirely accurate description, sublimation may be conveniently modeled as a sequential two-step process of melting followed by vaporization in order to apply Hess's law. Viewed in this manner, the enthalpy of sublimation for a substance may be estimated as the sum of its enthalpies of fusion and vaporization, as illustrated in Figure 1028. For example, heating and cooling curves. In the chapter of thermic chemistry, the relation between the amount of heat absorbed or released by a substance Q and its accompanying temperature change delta T was introduced. Q equals mc delta T, where m is the mass of the substance and c is its specific heat. The relation applies to matter being heated or cooled, but not undergoing a change in state. When a substance being heated or cooled reaches a temperature corresponding to one of its phase transitions, further gain or loss of heat is a result of diminishing or enhancing intermolecular attractions, instead of increasing or decreasing molecular kinetic energies. While a substance is undergoing a change in state, its temperature remains constant. Figure 1029 shows a typical heating curve. Consider the example of heating a pot of water to boiling. A stove burner will supply heat at a roughly constant rate. Initially, this heat serves to increase the water's temperature. When the water reaches its boiling point, its temperature remains constant despite the continued input from heat from the stove burner. This same temperature is maintained by the water as long as it is boiling. If the burner setting is increased to provide heat at a greater rate, the water temperature does not rise. But instead, the boiling becomes more vigorous. This behavior is observed for other phase transitions as well. For example, temperature remains constant while the change of state is in progress. Okay, a minute, I'm going to get the sweatshirt back on. Ouch. And once I finish this chapter, I'll go ahead and start dialysis for the night. Actually, I'll go ahead and just bring that. All right. Let me just go ahead and start it now. Okay. 10.4, phase diagrams. By the end of this section, you will be able to explain the construction and use of a typical phase diagram, use phase diagrams to identify stable phases at given temperatures and pressures, and to describe phase transitions resulting from changes in these properties. Describe the supercritical fluid phase of matter. In the previous module, the variation of a liquid's equilibrium vapor pressure with temperature was described considering the definition of boiling point. Plots of vapor pressure versus temperature represent how the boiling point of the liquid varies with pressure. Also described was the use of heating and cooling curves to determine a substance melting or freezing point. Making such measurements over a wide range of pressures yields data that may be presented graphically as a phase diagram. A phase diagram combines plots of pressures, pressure versus temperature for the liquid gas, solid liquid, and solid gas phase transition equilibria of a substance. These diagrams indicate the physical states that exist under specific conditions of pressure and temperature, and also provide the pressure dependence of the phase transition temperatures. A typical phase diagram for a pure substance is shown as figure 1030. So basically, just pointing this out. So you have three phases. You have your solid, you got your liquid, you got your gas, you got your transition lines. So anywhere on this line, so you have pressure and temperature as part of your thing. So whenever the pressure is high enough, but the temperature is low enough, it tends to be a solid. And then there's a point, and then when when the temperature is high and the pressure is low, you tend to get a gas. And then in between, you got the liquid. And then you have two major points. You have your triple point, where you'll have all three modes, gas, liquid, and solid, in the same container. And then the critical point, right, and that is where it goes super critical. And I'm sure we'll talk about that. Okay. To illustrate the utility of these plots, consider the phase diagram for water shown in figure 1031. We can use the phase diagram to identify the physical state of a sample of water under specified conditions of pressure and temperature. For example, the pressure of 50 kilopascals and a temperature of negative 10 degrees Celsius corresponds to the region of the diagram labeled ice. Under these conditions, water exists only as solid ice, a pressure of 50 and 200 degrees Celsius. Water exists only in the gaseous state. Note that on the H2O phase diagram, the pressure and temperature axes are not drawn to a constant scale in order to permit the illustration of several important features as described here. The curve BC in figure 1031 is the plot of vapor pressure versus temperature as described in the previous module of this chapter. This liquid vapor curve separates the liquid and gaseous regions of the phase diagram and provides the boiling point for the water at any pressure. For example, at 1 atmosphere, the boiling point is 100 degrees Celsius. I'm going to pause for a sec. Okay. Indicating that the water cannot exist as a liquid above the temperature regardless of the pressure. Physical properties of water under these conditions are intermediate between those of its liquid and gaseous phases. This unique state of matter is called the supercritical fluid, a topic that will be described in the next section of this module. The solid vapor curve labeled AB in figure 1031 indicates the temperatures and pressures at which ice and water vapor are in equilibrium. These temperature-pressure data pairs correspond to the sublimation or deposition points for water. If we could zoom in on the solid gas line, figure 1031, we would see that ice has a vapor pressure of about 20 kilopascals at negative 10 degrees Celsius. Thus, if we place a frozen sample in a vacuum with a pressure less than 0.2 kilopascals, ice will sublime. This is the basis for the freeze-drying process, often used to preserve foods such as ice cream, shown in Figure 1032. The solid-liquid curve labeled BD shows the temperatures and pressures at which ice and liquid water are in equilibrium, representing the melting freezing points for water. Note that this curve exhibits a slight negative slope, indicating that the melting point for water decreases slightly as pressure increases. Water is an unusual substance in this regard, as most substances exhibit an increase in melting point with the increasing pressure. This behavior is partly responsible for the movement of glaciers, like the one shown in Figure 1033. The bottom of a glacier experiences an immense pressure due to the weight that can melt some of the ice, forming a layer of liquid water on which the glacier may more easily slide. The point of intersection of all three curves is labeled B in Figure 1031. At the pressure and temperature represented by this point, all three phases of water coexist in equilibrium. This temperature-pressure data pair is called the triple point. At pressures lower than the triple point, water cannot exist as a liquid, regardless of the temperature. I was wondering if liquid is maybe an intermediate phase, because water is like a solid, except for it's kind of stuck in the container. Consider the phase diagram for carbon dioxide shown in Figure 1034. As another example, the solid-liquid curve exhibits a positive slope, indicating that the melting point for CO2 increases with pressure, as it does for most substances. Water being a notable exception, as described previously. Notice that the triple point is well above 1 atmosphere, indicating that carbon dioxide cannot exist as a liquid under ambient pressure conditions. Instead, cooling gaseous carbon dioxide at 1 atmosphere results in its deposition into the solid state. Likewise, solid carbon dioxide does not melt at 1 atmosphere pressure, but instead sublimes to yield gaseous CO2. Finally, notice that the critical point for carbon dioxide is observed at a relatively modest temperature and pressure in comparison to water. Supercritical fluids. If we place a sample of water in a sealed container at 25 Celsius, remove the air, and let the vaporization condensation equilibrium establish itself, they are left with a mixture of liquid water and water vapor at a pressure of 0.03 atmosphere. A distinct boundary between the more dense liquid and the less dense gas is clearly observed. As we increase the temperature, the pressure of the water vapor increases, as described by the liquid gas curve in the phase diagram for water, and the two-phase equilibrium of liquid and gaseous phases remains. At the temperature of 374 degrees Celsius, the vapor pressure has risen to 218 atmospheres, and any further increase in temperature results in the disappearance of the boundary between liquid and vapor phases. All of the water in the container is now present in a single phase whose physical properties are intermediate between those of the gaseous and liquid states. This phase of matter is called a supercritical fluid, and the temperature and pressure above which this phase exists is the critical point. Above its critical temperature, a gas cannot be liquefied no matter how much pressure is applied. The pressure required to liquefy a gas at its critical temperature is called the critical pressure. The critical temperatures and critical pressures of some common substances are given in the following table. Like a gas, a supercritical fluid will expand and fill a container, but its density is much greater than typical gas densities, typically being close to those one sec. $70. They exhibit essentially similar to liquids, these fluids are capable of dissolving non-volatile solutes. They exhibit essentially no surface tension and very low viscosities. However, so they can more effectively penetrate very small openings in a solid mixture and remove soluble components. These properties make supercritical fluids extremely useful solvents for a wide range of applications. For example, supercritical carbon dioxide has become a very popular solvent in the food industry, being used to decaffeinate coffee, remove fats from potato chips, and extract flavor and fragrance compounds from citrus oils. It is non-toxic, relatively inexpensive, and not considered to be a pollutant. After use, the CO2 can be easily recovered by reducing the pressure and collecting the resulting gas. That's so cool. 10.5, the solid state of matter. By the end of the section, you'll be able to define and describe the bonding of properties of ionic, molecular, metallic, and covalent network crystalline solids. Describe the main types of crystalline solids: ionic solids, metallic solids, covalent network solids, and molecular solids. Explain the ways in which crystal defects can occur in a solid. When most liquids are cool, they eventually freeze and form crystalline solids. Solids in which the atoms, ions, or molecules are arranged in a definite repeating pattern. It is also possible for a liquid to freeze before its molecules become arranged in an orderly pattern. The resulting materials are called amorphous solids, or non-crystalline solids. The particles of such solids lack an ordered internal structure and are randomly arranged. Metals and ionic compounds typically form ordered crystalline solids. Substances that consist of large molecules. Sorry. Wow, another 3,000? Jeez. That's crazy. Okay. Metal and substance or mixture of molecules whose movements are more restricted often form amorphous solids. Depending on these conditions under which it is produced, also amorphous solids may undergo a transition to the crystalline state under appropriate conditions. Crystalline solids are generally classified according to the nature of the forces that hold its particles together. These forces are primarily responsible for the physical properties exhibited by the bulk solids. The following sections provide descriptions of the major types of crystalline solids: ionic, metallic, covalent network, and molecular. Ionic solids. Ionic solids such as sodium chloride and nickel oxide are composed of positive and negative ions that are held together by electrostatic attractions, which can be quite strong. Many ionic crystals also have high melting points. This is due to the very strong attractions between the ions. In ionic compounds, the attractions between full charges are much larger than those between the partial charges in polar molecular compounds. This will be looked at in more detail in a later discussion of lattice energies. Although they are hard, they also tend to be brittle, and they shatter rather than bend. Ionic solids do not conduct electricity. However, they do conduct when molten or dissolved because their ions are free to move. Many simple compounds formed by the reaction of a metallic element with a nonmetallic element are ionic. Metallic solids. Metallic solids, such as crystals of copper, aluminum, and iron, are formed by metal atoms. The structure of metallic crystals is often described as a uniform distribution of atomic nuclei within a sea of delocalized electrons. The atoms within such a metallic solid are held together by a unique force known as metallic bonding that gives rise to many useful and varied bulk properties. All exhibit high thermal and electrical conductivity, metallic luster, and malleability. Many are very hard and quite strong. Because of their malleability, the ability to deform under pressure or hammering, they do not shatter and, therefore, make useful construction materials. The melting points of the metals vary widely. Mercury is a liquid at room temperature, and the alkali metals melt below 200 degrees Celsius. Several post-transition metals also have low melting points, whereas the transition metals melt at temperatures above 1,000 degrees Celsius. These differences reflect differences in strengths of metallic bonding among the metals. Covalent network solid. Covalent network solids include crystals of diamond, silicon, and some other nonmetals, and some covalent compounds such as silicon dioxide and silicon carbide. Many minerals have networks of covalent bonds. The atoms in these solids are held together by a network of covalent bonds, as shown in Figure 1041. To break or to melt a covalent network solid, covalent bonds must be broken. Because covalent bonds are relatively strong, covalent network solids are typically characterized by hardness, strength, and high melting points. For example, diamond is one of the hardest substances known and melts above 3,500 degrees Celsius. Molecular solids. Molecular solids such as ice, sucrose, and iodine, as shown in Figure 1042, are composed of neutral molecules. The strengths of the attractive forces between the units present in different crystals vary widely, as indicated by the melting points of the crystals. Small symmetrical molecules, nonpolar molecules such as H2, N2, O2, and F2, have weak attractive forces and form molecular solids with very low melting points. Substances consisting of larger nonpolar molecules have larger attractive forces and melt at higher temperatures. Molecular solids composed of molecules with permanent dipole moments melt at still higher temperatures. Examples include ice and table sugar. Properties of solids. A crystalline solid like those listed in Table 10.4 has a precise melting temperature because each atom or molecule of the same type is held in place with the same forces or energy. Thus, the attractions between the units that make up the crystal all have the same strength and all require the same amount of energy to be broken. The gradual softening of an amorphous material differs dramatically from the distinct melting of a crystalline solid. This results from the structural non-equivalence of the molecules in the amorphous solid. Some forces are weaker than others, and when an amorphous material is heated, the weakest intermolecular attractions break first. As the temperature is increased further, the stronger attractions are broken. Thus, amorphous materials soften over the range of temperatures. Crystal defects. In a crystalline solid, the atoms, ions, or molecules are arranged in a definite repeating pattern, but occasional defects may occur in the pattern. Several types of defects are known as illustrated in Figure 1045. Vacancies are defects that occur when positions that should contain atoms or ions are vacant. Less commonly, some atoms or ions in a crystal may occupy positions called interstitial sites, located between the regular positions for atoms. Other distortions are found in impure crystals, as for example, when the cations, anions, or molecules of the impurity are too large to fit into the regular positions without distorting the structure. Trace amounts of impurities are sometimes added to a crystal, a process known as doping, in order to create defects in the structure that yield desirable changes in its properties. For example, silicon crystals are doped with varying amounts of different elements to yield suitable electrical properties for their use in the manufacture of semiconductors and computer chips. All right, 10.6, lattice structures and crystalline solids. By the end of this section, you'll be able to describe the arrangement of atoms and ions in crystalline structures, compute ionic radii using unit cell dimensions, explain the use of X-ray diffraction measurements in determining crystalline structures. Over 90% of naturally occurring and man-made solids are crystalline. Most solids form with a regular arrangement of their particles because the overall attractive interactions between particles are maximized and the total intermolecular energy is minimized. When the particles pack in the most efficient manner, the regular arrangement at an atomic level is often reflected at a macroscopic level. In this module, we will explore some of the details about the structures of metallic and ionic crystalline solids and learn how these structures are determined experimentally. The structure of metals. We will begin our discussion of crystalline solids by considering elemental metals, which are relatively simple because each contains only one type of atom. A pure metal is a crystalline solid with metal atoms packed closely together in a repeating pattern. Some of the properties of metals in general, such as their malleability and ductility, are largely due to having identical atoms arranged in a regular pattern. The different properties of one metal compared to another partially depend on the sizes of their atoms and the specifics of their spatial arrangements. We will explore the similarities and differences of four of the most common metal crystal geometries in the sections that follow. Unit cell of metals. The structure of a crystalline solid, whether a metal or not, is best described by considering its simplest repeating unit, which is referred to as its unit cell. The unit cell consists of lattice points that represent the location of atoms or ions. The entire structure then consists of this unit cell, repeating in 3 dimensions as illustrated in Figure 1046. Let us begin our investigation of crystal lattice structure in unit cells with the most straightforward structure and the most basic unit cell. To visualize this, imagine taking a large number of identical spheres, such as tennis balls, and arranging them uniformly in a container. The simplest way to do this would be to make layers in which the spheres in one layer are directly above those in the layer below, as illustrated in Figure 1047. This arrangement is called simple cubic structure, and the unit cell is called the simple cubic unit cell, or primitive cubic unit cell. Man, I remember this used to confuse the shit out of me, but I totally get it now. I can't wait to describe it. In a simple cubic structure, the spheres are not packed as closely as they could be, and they only fill about 52% of the volume of the container. This is relatively inefficient. This is a relatively inefficient arrangement, and only one metal, polonium, crystallizes in a simple cubic structure, as shown in Figure 1048. A solid with this type of arrangement consists of planes or layers in which each atom contracts only the four nearest neighbors in its layer, one atom directly above it in the layer above, and one atom directly below it in the layer below. The number of the particles that each particle in a crystalline solid contact is known as its coordination number. For a polonium atom in a simple cubic array, the coordination number is therefore 6. In a simple cubic lattice, the unit cell that repeats in all directions is a cube defined by the centers of 8 atoms, as shown in Figure 1049. Atoms at adjacent corners of this unit cell can contact each other, so the edge length of the cell is equal to 2 atomic radii, or 1 atomic diameter. A cubic unit cell contains only the parts of these atoms that are within it. Since an atom at a corner of a simple cubic unit cell is contained by a total of 8 unit cells, only 1/8 of that atom is within a specific unit cell. And since each simple cubic unit cell has one atom at each of its 8 corners, there is 8 times 1 over 8 equals 1 atom within one simple cubic unit cell. And I'll demonstrate that at some point. Okay. Most metal crystals are one of the 4 major types of unit cells. For now, we will focus on the 3 cubic unit cells: simple cubic, which we have already seen, body-centered cubic unit cell, and face-centered cubic unit cell, all of which are illustrated. Note that there are actually 7 different lattice systems, some of which have more than one type of lattice, for a total of 14 different types of unit cells. We leave the more complicated geometries for later in this model. Some metals crystallize in an arrangement that has a cubic unit cell with atoms at all of the corners and an atom in the center, as shown in Figure 1051. This is called a body-centered cubic solid. Atoms in the corners of a BCC unit cell do not contact each other, but contact the atom in the center. A BCC unit cell contains 2 atoms, 1/8 of an atom at each of the 8 corners, plus 1 atom in the center, from the center. Any atom in this structure touches 4 atoms in the layer above it and 4 atoms in the layer below it. Thus, an atom in a BCC structure has a coordination number of 8. Atoms in BCC arrangements are much more efficiently packed than a simple cubic structure, occupying about 68% of the total volume. Isomorphous metals with a BCC structure include K, Ba, Cr, Mo, W, and Fe at room temperature. Elements or compounds that crystallize with the same structure are said to be isomorphous. Many other metals, such as aluminum, copper, and lead, crystallize in an arrangement that has a cubic unit cell with atoms at all of the corners at the centers of each face, as illustrated in Figure 1052. This arrangement is called a face-centered cubic solid. A face-centered cubic unit cell contains 4 atoms, 1/8 of an atom at each of the 8 corners, and 1/2 of an atom on each of the 6 faces. The atoms at the corners touch the atoms in the centers of the adjacent faces along the face diagonals of the cube. Because the atoms are identical on identical lattice points, they have identical environments. Atoms in an FCC arrangement are packed as closely together as possible, with atoms occupying 74% of the volume. This structure is also called cubic closest packing. In CCP, there are 3 repeating layers of hexagonally arranged atoms. Each atom contacts 6 atoms in its own layer, 3 in the layer above, and 3 in the layer below. In this arrangement, each atom touches 12 near neighbors, and therefore has a coordination number of 12. The fact that FCC and CCP arrangements are equivalent may not be immediately obvious, but why they are actually the same structure is illustrated in 1053. Don't care. Because closer packing maximizes the overall attractions between atoms and minimizes the total intermolecular energy, the atoms in most metals pack in this manner. We find 2 types of closest packing in simple metallic crystalline structures: CCP, which we have already encountered, and hexagonal closest packing, HCP. shown in figure 1054. Both consist of repeating layers of hexagonally arranged atoms in both types. A second layer is placed on the first layer, so that each atom in the second layer is in contact with 3 atoms in the first layer. The third layer is positioned in one of 2 ways. In HCP, atoms in the third layer are directly above the atoms in the first layer, and the stacking consists of alternating type A and type B close-packed layers. In CCP, atoms in the third layer are not above atoms in either of the first 2 layers, and the stacking consists of alternating type A, type B, and type C close-packed layers. About 2/3 of all metals crystallize in closest packing arrays with coordination numbers of 12. Metals that crystallize in an HCP structure include Cd, Co, Li, Mg, and AzN, cadmium, cobalt, lithium, magnesium, sodium, zinc, and metals that crystallize in a CCP structure include silver, aluminum, calcium, copper, nickel, lead, and platinum. In general, a unit cell is defined by the lengths of the 3 axes A, B, and C, and angles alpha, beta, and gamma between them. As illustrated in figure 1055, the axes are defined as being the lengths between points in the space lattice. Unit cell axes join points with identical environments. There are 7 different lattice systems, some of which have more than one type of lattice, for a total of 14 different unit cells, which have the shape shown in figure 1056. You got cubics, you got tetragonals, which is basically just a cubic that's longer on one side or shorter. Orthorhombic. Oh, okay, so tetragonals, 2 sides equal each other. Clinic. Okay. The structures of ionic solid crystals, or ionic crystals. Ionic crystals consist of 2 or more different kinds of ions that usually have different sizes. The packing of these ions into a crystal structure is more complex than the packing of metal atoms that are the same size. Most monatomic ions behave as charged spheres, and their attraction for ions is opposite charge is the same in every direction. Consequently, stable structures for ionic compounds result when ions of one charge are surrounded by as many ions as possible of the opposite charge, and when the cations and anions are in contact with each other. Structures are determined by 2 principal factors: the relative sizes of the ions and the ratio of the numbers of positive and negative ions in the compound. In simple ionic structures, we usually find the anions, which are normally larger than the cations, arranged in a closest packed array. The smaller cations commonly occupy one of 2 types of holes remaining between the anions. The smaller of the holes is found between 3 anions in one plane and 1 anion in an adjacent plane. The 4 anions surrounding this hole are arranged at the corners of a tetrahedron, so the hole is called a tetrahedral hole. A larger type of hole is found at the center of 6 anions, 3 in one layer and 3 in an adjacent layer. Located at the corners of an octahedron, this is called an octahedral hole. Figure 1057 illustrates both these types of holes. Depending on the relative sizes of the cations and anions, the cations of an ionic compound may occupy tetrahedral or octahedral holes. And as illustrated in figure 1058, relatively small cations occupy tetrahedral holes, and larger cations occupy octahedral holes. If the cations are too large to fit in the octahedral holes, the anions may adopt a more open structure, such as a simple cubic array. The larger cations can then occupy the larger cubic holes, made possible by the more open spacing. There are 2 tetrahedral holes for each anion in either an HCP or CCP array of anions. A compound that crystallizes in a closest packed array of anions with cations in the tetrahedral holes can have a maximum cation-anion ratio of 2:1. All of the tetrahedral holes are filled at this ratio. Examples include lithium oxide, sodium oxide, lithium sulfide, and sodium sulfide. Compounds with a ratio of less than 2:1 may also crystallize in a closest packed array of anions with cations in the tetrahedral holes. If the ionic sizes fit, in these compounds, however, some of the tetrahedral holes remain vacant. The ratio of octahedral holes to anions in either an HCP or a CCP structure is 1:1. Thus, compounds with cations and octahedral holes And the closest packed array of anions can have a maximum cation-anion ratio of 1 to 1. And nickel oxide, manganese sulfide, manganese 2 sulfide, uh, so, sodium chloride, and potassium hydride, for example, all of the octahedral holes are filled. Ratios of less than 1 to 1 are observed when some of the octahedral holes remain empty. In a simple cubic array of anions, there is one cubic hole that can be occupied by a cation for each anion in the array. In cesium chloride and in other compounds with the same structure, all of the cubic holes are occupied. Half of the cubic holes are occupied in strontium hydride, uranium-4 oxide, strontium chloride, and calcium fluoride. Different types of ionic compounds often crystallize in the same structure when the relative sizes of their ions and their stoichiometries, the two principal features that determine structure, are similar. Unit cells of ionic compounds. Many ionic compounds crystallize with cubic unit cells, and we will use these compounds to describe the general features of ionic structures. When an ionic compound is composed of cations and anions of similar size in a 1 to 1 ratio, it typically forms a simple cubic structure. Cesium chloride is an example of this, with the cesium plus and chloride minus ions having radii of 174 picometers and 181 picometers respectively. We can think of this as chloride ions forming a simple cubic unit cell with a cesium ion in the center, or as cesium ions forming a unit cell with a chloride ion in the center, or as simple cubic unit cells formed by cesium ions overlapping unit cells formed by chloride ions. Cesium ions and chloride ions touch along the body diagonals of the unit cells. One cesium ion and one chloride ion are present per unit cell, giving the 1 to 1 stoichiometry required by the formula for cesium chloride. Note that there is no lattice point in the center of the cell, and cesium chloride is not a BCC structure because a cesium ion is not identical to a chloride ion. We have said that the location of lattice points is arbitrary. This is illustrated by an alternate description of the CSCl structure in which the lattice points are located in the centers of the cesium ions. In this description, the cesium ions are located on the lattice points at the corners of the cell, and the chloride ion is located at the center of the cell. The two unit cells are different, but they describe identical structures. When an ionic compound is composed of a 1 to 1 ratio of cations and anions that differ significantly in size, it typically crystallizes with an FCC unit cell, like that shown in figure 1060. Sodium chloride, NaCl, is an example of this, with the sodium and chloride ions having radii of 102 and 181 picometers respectively. You can think of this as chloride ions forming an FCC cell, with sodium ions located in the octahedral holes in the middle of the cell edges and in the center of the cell. The sodium and chloride ions touch each other all along the cell edges. The unit cell contains 4 sodium ions and 4 chloride ions, giving the 1 to 1 stoichiometry required by the formula NaCl. The cubic form of zinc sulfide, zinc blende, also crystallizes in an FCC unit cell. As illustrated in figure 1061, this structure contains sulfide ions on the lattice points of an FCC lattice. The arrangement of sulfide ions is identical to the arrangement of chloride ions in sodium chloride. The radius of a zinc ion is only about 40% of the radius of a sulfide ion, so these small zinc 2 ions are located in alternating tetrahedral holes, that is, in one half of the tetrahedral holes. There are 4 zinc ions and 4 sulfide ions in the unit cell, giving the empirical formula ZnS. A calcium fluoride unit cell, like that shown in figure 1062, is also an FCC unit cell, but in this case, the cations are located on the lattice points. Equivalent calcium ions are located on the lattice points of an FCC lattice. All of the tetrahedral sites in the FCC array of calcium ions are occupied by fluoride ions. There are 4 calcium ions and 8 fluoride ions. In a unit cell, giving a calcium-fluorine ratio 1 to 2, as required by the chemical formula CaF2. Close examination of figure 1062 will reveal a simple cubic array of fluoride ions with calcium ions in one half of the cubic holes. The structure cannot be described in terms of a space lattice of points on the fluoride ions because the fluoride ions do not all have identical environments. The orientation of the four calcium ions about the fluoride ions differs. Calculation of ionic radii. If we know the edge length of a unit cell of an ionic compound and the position of the ions in the cell, we can calculate ionic radii for the ions in the compound if we make assumptions about individual ionic shapes and contacts. It is important to realize that values for ionic radii calculated from the edge lengths of unit cells depend on the numerous assumptions such as perfect spherical shape for ions, which are approximations at best. Hence, such calculated values are themselves approximate, and comparisons cannot be pushed too far. Nevertheless, this method has proved useful for calculating ionic radii from experimental measurements such as X-ray crystallographic determinations. X-ray crystallography. The size of a unit cell and the arrangement of the atoms in a crystal may be determined from measurements of the diffraction of X-rays by the crystal. Termed X-ray crystallography, diffraction is a change in the direction of travel experienced by an electromagnetic wave when it encounters a physical barrier whose dimensions are comparable to those of the wavelength of light. X-rays are electromagnetic radiation with wavelengths about as long as the distance between neighboring atoms and crystals, on the order of a few angstroms. When a beam of monochromatic X-ray strikes a crystal, its rays are scattered in all directions by the atoms within the crystal. When scattered waves traveling in the same direction encounter one another, they undergo interference, a process by which the waves combine to yield either an increase or a decrease in amplitude, depending upon the extent to which the combining waves' maxima are separated. When X-rays of a certain wavelength lambda are scattered by atoms in adjacent crystal planes, separated by a distance d, they may undergo constructive interference when the difference between the distances traveled by the two waves prior to their combination is an integer factor n of the wavelength. This condition is satisfied when the angle of the diffraction beam theta is related to the wavelength and interatomic distance by the equation n lambda equals 2d sine theta. This relation is known as the Bragg equation in honor of W. H. Bragg, the English physicist who first explained this phenomenon. Figure 1064 illustrates two examples of diffracted waves from the same two crystal planes. The figure on the left depicts waves diffracted at the Bragg angle, resulting in constructive interference, while that on the right shows diffraction at a different angle that does not satisfy the Bragg condition, resulting in destructive interference. An X-ray diffractometer, such as the one illustrated in figure 1065, may be used to measure the angles at which X-rays are diffracted when interacting with a crystal as described earlier. From such measurements, the Bragg equation may be used to compute distances between atoms as demonstrated in the following example exercise. And that's it. Chapter 10.